important class of distributed memory algorithmic primitives are the so-called collective operations. No, not that kind of collective. One example of a collective operation is a reduction, which in the distributed memory case I will call all-to-one reduce. The phrase all-to-one makes it clear that all nodes participate to produce a final result on one node. Let's take an example. Consider this linear network, which I've numbered from 0 to 8. These ID numbers I'll sometimes call ranks. So for example, the rank of this node is 4. Now suppose each node has a single value in its private memory. Let's say these values. In an all-to-one reduction, you want to produce a final result, which is the reduction, in this case sum of all the values, on a root node. So the sum of these values, it turns out, is 55, and let's say we want that result to appear on node 0. Now intuitively, you expect a tree-based scheme like this one to work well. Its span is logarithmic in the size of the input. In this case, there are p-values. Now this observation suggests that you'll need to perform at least log p communication steps. Now initially, the data is distributed across all nodes, so no node can do any actual work. Therefore, you'll need to do some communication. Okay, well that's easy. Let's have all the odd-numbered nodes send their data to their leftmost neighbor. So 1 will send to 0, 3 will send to 2, and so on. None of these sends conflict, so all the sends can happen simultaneously. So this round of communication will cost you alpha plus beta time since you're only sending one word. After the communication, the even ranks add the incoming value. The new state of the system then looks like this. Now in this next step, you'll notice that only even-numbered ranks have values. So notice the even ranks have partial sums. So we can repeat this scheme, except this time with odd partners of the remaining set sending to the closest even partner. So we might do these sends, for example. Again, there are no conflicts in the paths, so this costs us alpha plus beta time. And you'll just repeat this process until a final result remains. Now to implement this scheme, I want to point out a useful fact. Suppose we replace the ranks by their equivalent binary strings. Recall that in the first round, the odds send to the evens. Notice, the odds all have a 1 in their least significant bit, and the evens all have 0. In the next round, the only participating processes have a 0 in their least significant bit. And notice what happens. Nodes with a 1 in their second bit send to nodes who have a 0 in their second bit. So again, it's basically odds to evens where you drop off the last bit. Neat. If you've heard of things like hypercubes, binary reflected gray codes, or Hamming distances, then this bit manipulation or bit view of the world will seem very familiar. And if you aren't, we'll give you some pointers in the instructor's notes. Shave and a haircut, 2 bits. I don't know what that shave and a haircut 2 bits thing is, but I got it from somewhere.